All right, so we our class. Start our class from where we stopped uh, on Wednesday. Remember, this is the study of hydrodynamics, which is the study of fluid in motion. So on Wednesday, just a recap, we talked about the assumption of an ideal fluid, which are basically four. Fluid, the first one is fluid is non-viscous, fluid is incompressible, um, the fluid motion is steady, and then the fluid is irrotational. These are the four assumptions of ideal fluid. And then types of fluid. We mentioned this last on Wednesday that we have two types of fluid flow, laminar and turbulent flow. And then how to determine laminar and turbulent flow is by the use of Reynolds number. And we talked about the importance of viscosity and the resistance to fluid flow. We discussed about flow rate. Q is equal to V over T. That is the volume of fluid crossing a given path at a given time. And then we derive our continuity equation from the flow rate equation as A1 V1 is equal to A2 V2. A is area 1, V1 is velocity 1 or speed 1, and then at the second part we have A2 V2, A2 for area 2 and V2 for the speed or the flow of the fluid 2. Then we discussed about mass flow rate, which is given there rho AV. We solve some examples and move on to Bernoulli's principle, which is a principle that relates speed and pressure. So according to Bernoulli's principle, the velocity or speed of flow of a fluid in a given direction is inversely proportional to pressure. So if the speed is high, then the pressure will be low. If the pressure increases, the speed will decrease. And the equation or the principle for the Bernoulli's, the equation for Bernoulli's principle is given as P, that is pressure, the kinetic energy of the fluid per unit volume, and then the potential energy of gravitational potential energy of the fluid per unit volume is constant. So if we have a system that has that is elevated, such as this figure, then we will have Bernoulli's equation applied to both sides. So in that case, we are going to have P1 plus half rho V1 square plus rho G Y1 is equal to P2 plus half rho V2 square plus rho GY2. So that is Bernoulli's equation. And we apply this equation to Venturi tube. So for a Venturi tube is a horizontal pipe, a pipe that is made horizontally. There is no height difference. So since there is no height difference, it simply implies that the height parameter in Bernoulli's equation becomes 0 because at the entering point of the fluid and the exit point of the fluid, the heights are the same. So the difference in the height becomes 0. So the height parameter in Bernoulli's expression becomes 0. So we are going to have an abbreviation of Bernoulli's equation as P1 plus half rho V1 square is equal to P2 plus half rho V2 square. Now, with this expression, if we are asked to find the speed at which the fluid is flowing, either entering or leaving, if one of the speed is known, that is, if we know the speed at which the fluid is entering, we can determine the speed at which the fluid is leaving. And even if we don't know the speed at which the fluid is entering, we can determine the speed at which the fluid is leaving. So in that case, we are going to apply both the abbreviation of Bernoulli's equation as applied to Venturi tube and then the continuity equation. So let's look at that. The continuity equation, according to the continuity equation, we have A1 V1 is equal to A2 V2. So if we make V1 the subject of the formula, we are going to have V1 is equal to A2 V2 over A1. So now, if we take that expression and substitute into the abbreviated version of the Bernoulli's equation for Venturi tube and replace V1 square with that continuity equation there in terms of V2, we will have an expression such as this. So V, by the time you simplify the expression further to the final stage, we have V is equal to A1 square root of 2 change in pressure all over density, then change in the area square. So that is what we are going to have. Now, Bernoulli's equation or principle can also be applied to a system that will give us, lead us to Torricelli's law. Now, look at that system, that diagram beside you is considered as a tank containing a liquid of density that has a small hole by the side. Imagine you having a table water, and then you are so sure that the table water is not leaking, but all of a sudden you drop it on the table and you discover that there is water on the table. You raise a bottle and then look around that there is no evidence of the plastic leaking anywhere. You clean the table and then clean the bottom of the plastic and then drop it again. After some minutes, by the time you raise the plastic bottle, you notice water again. But when you raise the plastic, you can't see evidence of where the water is actually leaking. So in a situation like that, that is where Torricelli's law comes, is applicable. So if we see a tank containing a liquid of density has a small hole in it at a side at a distance y1 from the bottom. The air above the liquid is maintained at a pressure P. We can determine the speed